Okay. Something I forgot to write, but then this way I can put it there and you don't need to write it. You can find it in any book. That's the super Virasoro algebra. So remember the L's are the modes of the energy momentum tensor, and the GR or Fn are the modes of the supercurrent. And they commute, I mean, it makes sense. L and L gives you L, L and G gives you another G, and then G and G gives you L. So commutation relations that make sense. Okay, so now physical states. And we'll start with the open string. And then the closed string is tensor product of the. So we say how we build the states. We act with alphas and with B's or with E's, depending if you're on the Neves-Schwarz or the Ramon sector. And the physical state conditions are Lm phi equals 0 for all m greater than 0. L0 phi equals to A phi, and computation that it's in the homework. So A depends in what sector you are. In the Ramon sector is 0, and the intuition is that the 0-point energy of the bosons cancels with the 0-point energy of the worst bosons cancels with the 0-point energy of the worst fermions. Here, because they both have periodic boundary conditions. So bosons are always periodic, and in the Ramon sector, the fermions are periodic. And so they cancel, while here they are anti-periodic. So what you get, they partially cancel, so it's less than in the bosonic string, but not completely. So here what you get is d minus 2 over 16. This d minus 2 comes from doing, so again, you have things like eta mu mu when you do the commutators, and this you have to replace by delta II. So this Lycon gauge quantization that we talked about in the bosonic string also works here. And also to count number of physical states in a quick and dirty way, whenever you see an alpha mu or B mu or D mu, you just replace it by an I, and then that will give you the right number of physical states. The right number of states. We're going to get that from requiring the physical state conditions up to the massless level. We won't work. So for d equals 10 and d equals 10, you get from the ghost, the part that I didn't explain. So then this is 1/2. So ANS is 1/2 and A Ramon is equal to 0. So depending whether the state is NS or Ramon, you have to put a different A. And then in the Ramon sector, you have that Fn phi equals 0 for all n greater or equal than 0. So also F0 phi is equal to 0, and we'll see how that condition looks like. And in the NS sector, well, here there is not much doubt because this starts from R equals 1/2. So those are the physical state conditions which come from the constraints. Which come from the constraint. So let's start building the spectrum. Yeah, so let's start with the NS sector. So we start at n equals 0. So this NS ground state, which is annihilated by all alphas, and so I don't have to put it right there. Well, alpha mu m on 0 is equal to 0 for all m greater than 0. Well, let me not put it, or maybe I even wrote it. It's annihilated by all the annihilation operators. So then it's trivial to see that this is true. And this one here, so L0 phi is equal to ANS phi, which is 1/2 of phi. Sorry, well, that's true in general, but now where phi is the 0 NS. So L0 is this, so 1/2 of alpha 0 square plus the sum. So we are in the NS sector. R equals 1/2 to infinity of RB minus RBR. Yeah, I'm not missing 1/2, right? Yeah, no, I'm not missing 1/2. So this is the same as before. It's going to give me p squared alpha prime p squared. And this operator here is a number operator. That will, well, I started saying n equals 0. Okay. I mean, it's the same as in the bosonic string. And this will count the number of oscillations that you have, counting this and this. And since there is no, in the anti-commutation relation, so VR, S is equal to delta R plus S0, well, mu and mu. Since here there is no R, then it's important that this R appears here, because that will really count the level. So if we do it in general, so the condition, let me do it in general, not for the vacuum. The condition L0 phi equals A phi is going to tell us, and this p squared, the eigenvalue is k squared, which is equal to minus m squared. So this is going to tell us that the mass square is 1 over alpha prime and minus A. So we have a tower of states. That are separated at levels 1 over alpha prime, the same as in the bosonic string. So what does this tell you about, what does this tell us about this ground state? A in the NS sector is equal to 1/2. So this is saying that this is minus 1 over 2 alpha prime. So tachyon again. The difference is that there is a projection that I'll do in 5-10 minutes, that one can do consistent in the whole spectrum that gets rid of the tachyon. And there is no such equivalent thing in the bosonic string. So it's not that the tachyon does not show up, it does show up, but one can project it out. One can take the spectrum without the tachyon and with, we'll see how it works. Okay, so yeah, so if I have a alpha mu 1 minus 3, B, suppose you are in the n sector, B minus 1/2 nu, B minus 5/2 nu, this will count the sum of this. So this will give me 3, 3, 6. This is a state that is at level n equals 6. So you can have mixed alphas and Bs. And then, I mean, I didn't do it, but if you do it, you'll see, I mean, if you do it, you'll see that this is what happens. And because you have this R, this counts. So here, the number 3 will come from when you exchange this alpha 3 with this alpha minus 3. And because of the commutator that has, so alpha n, alpha mu n, alpha nu m is n delta then n plus m0. While here this anti-commute, but there's the 5/2 will come from here. I mean, I guess one has to do it to get convinced, but it. Okay, so what's the next level in the NS sector? One half. Right here in the NS sector, one can have integer or half integer n's. And this is B mu minus 1/2 acting on 0 ns. And polarization. So the L0 condition, L0 phi equals A phi, or 1/2 of phi. This will tell me that this state is massless, right? Okay, nice, massless vector. We like that. The next, so so then the next LM is L1. So L1 phi, do I have the L's written there? No, I have a, well, let me write the L's and the F's and the, so LM is 1/2 n equals minus infinity to infinity alpha n plus m. One can write it in different ways, and I don't remember yet. Maybe this is not the best way. Alpha n. I mean, they're all the same, but the sum of these two has to be m. And sorry, and I'm missing the fermion part. So if we're in the NS sector, this is the sum over R from minus infinity. Well, let me make sure about the factors. I think the factor is 1/2. No, it's not 1/2, sorry, it's n. Yeah, overall 1/2, but then also n plus r plus m over 2, and then b minus r, br, or the same thing, but with instead of an r, an m. And better say r in z plus 1/2, more than from minus infinity to infinity. So, or 1/2 of the sum over n instead of n plus m over 2, b minus n. No, and this is, yeah, I'm missing the br plus m. Sorry, I was missing the m, the n plus m. And of course, I didn't write it the same way as there, but it's the same. So let me write it like this. So they are all in the same, written in the same way. And the Fm is the sum of alpha n instead of alpha minus n, and these are the d's, the m plus n, and there's always a contraction, right? The mu and the mu index are contracted, and the gr is the sum over n also, alpha minus n, b m plus, sorry, r plus n. Okay, so it's not hard to see that. So L1, well, this part you can believe me that it will annihilate that. The alpha just commute. And this part, it will have, so there is a 1 here, so when r is equal to 1/2, and you have a, so when r is equal to 1/2, then this is b3/2, and when r is equal to minus 1/2, this is b1/2, but this is b1/2 as well. So it's not hard to see that this is equal to 0, and in general, that this is trivially satisfied, doesn't give any condition. The one that will give, it's also easy to see that gr phi is equal to 0 for all r greater or equal than 3/2. For the same reasons, but g1/2 is not trivial. g1/2 phi, so is this sum, but the only one that is going to give something non-trivial is when this is 1/2, and that's for n equals 0, right? So the only one that gives something non-trivial is alpha 0 b1/2, right? So let me put the indices nu acting on E mu b mu minus 1/2 0 and s. And now I commute these two, anti-commute, sorry. Whenever this one is acting here, I get a 0. And the anti-commutator gives just a delta of mu nu, right? And then the alpha 0 gives me a k. So this is equal to 0 if E mu, K mu is equal to 0. So exactly the same condition as we got in the bosonic string. So this is a massless vector. Polarization has to be orthogonal to K. There are null states. So K mu, B mu minus 1/2 on 0 ns is a null state. So E mu is E mu plus K mu. So it's exactly the same story as in the bosonic string. The only difference is that the one in the bosonic string was constructed with an alpha. And we can also construct that vector. We can also put an alpha here. But if we go there, A is equal to 1/2. If n is equal to 1, then that's massive. So the state that is E mu alpha mu, so this state, let me write it here. So this state is a vector, but it's massive. Its mass is 1/2 alpha prime. So it's at the next level, n equals 1. Okay, so this is then a massless vector and has a gauge field, so it's the field is a mu. And this tells us that a mu is the same as a mu plus d mu lambda. So exactly as in the bosonic string. And if I go one more level, though I'm not going to do the physical state conditions, but just we can count the number of states by doing this Lycon thing. But what states do I have at this level? So phi equals E mu alpha mu minus 1 on 0 ns. Or I can also have two B's, right? E mu nu, B mu minus 1/2, B nu minus 1/2, 0 ns. You work hard with the physics. So first, these states have mass. Well, as I just wrote it, but I just, erased it. But it's 1/2 alpha prime, right? And if I want to count the degrees of freedom, I have to put an I here, so there are 8 plus, now this is anti-symmetric, right? Because this is anti-commute. So it's 8 times 7 divided by 2, which is 28, right? Yeah. So 36 degrees of freedom. So if you work hard and do the physical state conditions, you should have the same. So this is, I'm doing here, this Lycon gauge. Lycon gauge counting, replacing the mu by an I index. Okay, and we can keep going. So the next level will be n equals 3/2, etc. So we have a tower of massive states. They start from the tachyon, minus 1 over 2 alpha prime. Then there is this massless vector, 1 over 2 alpha prime. So the separation is 1/2, 1 over 2 alpha prime between all these states, and it starts from the tachyon, but as we said, that's not a problem. I mean, that's not a problem. So we know how to fix that problem. Yes. No, somebody was asking what does this n count? So I wrote, for example, a state like this, and then it counts 1/2 plus 1/2. Yeah. Okay, well, maybe. I don't know, the same. Okay, now Ramon sector. So we start at n equals 0, 0 Ramon. So this 0 is not a very good notation because we know this is a space-time spinor. The book uses A, which is, I don't know, not great. But this goes from 1 to 32. So a spinor in 10 dimensions has 32 components, and these are 32 real components. And if we go there, A Ramond, I don't know, it was somewhere, A Ramond is equal to 0. So this state is massless. It's a massless spinor. Now, does it satisfy the physical state conditions? Well, the L0 condition is this condition. 0 Ramond, or let me call it A Ramond, equals 0. This is obvious that, so the lemma there. It's obvious that this is going to be 0. There's always one annihilator. And from the Fm, the only one that is going to give me a non-trivial condition is F0, because all the others will have either the alphas or the Ds will annihilate this state. So Fm A Ramond equals 0 for all m greater than 0. This is trivially satisfied. And I have to see the F0 condition. Yeah, A is just because when one puts 0, you think of a single state of a scalar, and there are 32 states here. So I could level them by the spin up and down, or plus, maybe better. Plus minus 1/2, plus minus 1/2. Yeah, this is better, and we're going to use that. So the 32 are constructed this way. So 2 to the 5. So this could be, I mean, they all have the same energy, it's degenerate. So this could be plus, 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 plus. Or this could be minus, 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 minus. It's a degenerate vacuum. One could define, if you wanted, the ground state to be the one that has all minuses. But okay, then you get another. You raise one of those pins and you get another state that has is massless and satisfies. Well, we'll see the physical state conditions. We haven't seen them yet. So okay, so what is this F0? What is F0 acting on this? F0, well, Fm are there. The only one that will give out of that sum, the only one that will give something non-trivial is for n equals 0. Right, so this is alpha 0, the 0, and let me put the indices. So acting on this state A, Ramon. And do you see what this is? So what does alpha 0? So this is Dirac equation, right? Alpha 0. So this is up to a coefficient. Alpha 0 acting on this gives me, so this commute, so I can put alpha 0 is going to give me a k nu. And this 0 was a gamma matrix. So, or let me put it like this. K nu or K mu gamma mu. So now gamma mu has two indices, A, B, acting on B, or, well, let me not write spinor indices. K mu gamma mu acting on this is equal to 0. And this is Dirac's equation. So it's a massless spinor that satisfies Dirac's equation. And what does that mean? So I can take, since it's massless, we can do the same as we did for the vector, taking K mu to be K, and then zeros in all the 8 other components. And this means K times gamma 0 plus gamma 1 has to be equal to 0. Acting on this A Ramon has to be equal to 0. And this is the gamma, so this is erasing, this raises the spin this raises this first spin. So this is telling me that the spin in this direction has to be negative. So then this implies that this state is actually minus 1/2, and then the others can be anything. By the chirality along this light cone coordinate, that is where the K is fixed. 1, 2, 3, 1, 2, 3, 4, 5. So this is fixed to be minus 1/2. Or plus 1/2, well, I don't know, well, I guess I said this is racing, so then if we say that's racing, then this is plus 1/2. It's convention. But now, so then I don't have 32, but I have 16 degrees of freedom. On-shell degrees of freedom, right? This is like an on-shell condition. Okay, so this state is physical, and what this F0 condition tells me is that it should satisfy Dirac's, it's massless. This is the L0 condition, and it should satisfy Dirac equation. So nice, makes sense. And I will collect then, I will collect everything in a table and put names to the fields corresponding to this. And if we go to the next level, so the next level is n equals 1. Here we don't have half integer n. And this I can do with an alpha mu minus 1. Acting on this A Ramon, or I can do it with a D mu minus 1 A Ramon. Right, both give me. So I have two vectors. If I want to count degrees of freedom, this should be 16. Sorry, 16. 16 times this. So 16 times 16, because there will be a physical state condition that will tell you about the chirality of this along K. So, okay, but I'm not. And this has m squared equals 1 over alpha prime. Right, it has n equals 1 and A is equal to 0. So in the Ramon sector, we get a tower of states, but it's more the space between states is twice the other, and it starts at m squared equals 0. Okay, so let's put everything together in S and Ramon sector. So in the NS sector, and let's not do it by level, but let's do it by mass. Because the A is not the same, then it makes more sense to compare them by mass. So here we have the NS vacuum. And in the Ramon sector, we don't have anything tachyonic. Then in the NS sector, we have this vector. These are 8 degrees of freedom. And not to confuse with spinor representations, I could put colors, but I put a V, and that's how it's called. It's the vector representation of SO8, which is the little group for this. And here is this A Ramon, and it has 16 degrees of freedom. If I want to see a spinors of SO8, which it is, right, because this chirality is fixed, so spinors of spin 8, then I have positive and negative chirality. Positive chirality, so this decomposes into 8 and 8. These are real degrees of freedom, because the spinor is Mariana. And so these are 8 is called S, the positive chirality, and 8C, negative chirality. So again, these are representations of SO8. Then I go to the next level. And here I have this alpha mu, E mu, alpha mu minus 1 on 0 ns, or the two b's 0 ns, while here I don't have anything. And at m squared equals 1 over alpha prime, here we said we have 2 times, so, well, let me not, well, okay, we have it there. So it's the number of degrees of freedom is 2 times 8 times 16, which is, you tell me, oh, I have it here, 256. Well, if you do the states here, what can you have? You can have an alpha and a b. So this is, here is at n equals 3/2 in the ns sector. To have mass equals to 1/2, so mass square, sorry, this is mass square, 1 over alpha prime n minus 1/2 in the ns sector. So to have mass 1 over alpha prime, we need n equals 3/2. So we can have this with an alpha and a b, or a b minus 3/2, or 3 b's. 3 b's minus 1/2. I mean, it doesn't, you count the degrees of freedom with the, and you should get 128 doing the, let me do it quickly. The idea is that you see the point that this is not very supersymmetric in space-time. So this spectrum is not very nice. There is a tachyon, and it's not supersymmetric. Here I have 8 degrees of freedom, and here I have 16. Here I have 128, and here I have 256. So the point is that there is a projection that one can do consistently in the spectrum, such that it kills all these intermediate levels in the ns sector. And here it kills, so it keeps 1/2 of the degrees of freedom. And that projection is called GSO projection. So GSO because of the people that invented it. It's Gliosi, one said. Sherk and Olive, sorry, where do I have it? Two cells. Gliosi, Sherk and Olive. Sherk and Olive. So we're going to define a projection G, and such that we will only keep the states that satisfy this. We have to cook it up such that these states have a minus sign, and half of the states here have a minus sign. So, I mean, here, especially the way I wrote it, it's not very hard to guess what the GSO projection will be, right? Chirality, no? I want to get rid of one chirality. So in the Ramon sector, it will have the chirality matrix, the gamma 11, sort of the product of all the gammas. And I'm going to write it. But, and in the NS sector, what do I want? How can I distinguish the states I want to keep from the states that I want to kill? So I'm going to project. So I'm going to define this G and then project onto the phi satisfying. So the identity, yeah, but it's not a projection. So you're not projecting anything if G is the identity. So I haven't defined this operator. So I'm going to project onto state satisfying this for some projector G that we're cooking up. So this G in the Ramon sector will have a chirality. So I'm going to project onto positive chirality, let's say. It's convention. But it's a very good question. In the closed string, that will have a meaning, a physical meaning. Here is convention. And here, so what do I want to... Okay, let me tell you, since there are many things I want to discuss. But, I mean, if we look at level, this is n equals 0, this is n equals 1/2, this is n equals 1, this is n equals 3/2. So I want to kill all the ones that have an integer number n. Or if I look at it from the point of view of worksheet spinors and scalars, these worksheet fermions on bosons, this doesn't have any excitation, so this is a worksheet boson. This here has a worksheet fermion excitation. So from the point of view of the worksheet, this is a worksheet fermion. This has two fermions, and it has a boson, so this is a worksheet boson. So we alternate between bosons and fermions. So I want to cook up a projection that kills whatever has an even number of worksheet fermions. So here I have 0, here I have 2, 0, 2. In the next level, I will have 0, 2, or 4. And for that, let me define the worksheet fermion number. So the worksheet fermion number, which is F, is defined by similar to the n, but I don't put B mu minus R, or contraction, BR. Or in the Ramon sector, sum of n equals 1 to infinity, d minus n dn. So it's similar to the n, the one that counts the level, but I don't put an r or an n, because I don't care if this excitation is 3/2, 5/2, or as long as there is a single b, that makes it a worksheet fermion. And again, I don't care what is this, the level. I care about that the total level is odd or even. And again, I care about total level being odd or even, so I care about -1 to the f. So this is the operator that I want to put, that I have to put in our projection. So in the NS sector, this G is minus 1 to the F. But actually, I want to kill this that has F equals 0. So F equals 0, I want it to be odd under this projection. So what I do is minus 1 to the F plus 1. So that's the GSO projector in the NS sector. And that kills all this. That kills this state, all intermediate states. Yes. Because we can. It's something we choose to do, but it's something that there is no such operation. It's something that you can do consistently in all spectrum, and you have a GSO projected states, and you scatter them, and it's going to give you. So if you take all even states, you scatter them, and it gives you even states. So it's a projection that you can do consistently in all the spectrum, and it's a nice. I mean, one can think of, okay, how can I cut the spectrum? I want to cut the spectrum for some reason. Okay, let's do this operation. Oh, great, you can do it consistently. And then, yeah, but it won't be consistent. I mean, there is a, because you're right that there is another operator. In the heterotic theory, for example, you can cut in a different way, and you get the non-supersymmetric heterotic theory. But the point is that there are very, very, very few things that you can do which are consistent. This is one of them. And this is consistent and preserves supersymmetry and gets rid of the tachyon. In the heterotic theory, there's something that you can do consistently. You project out of the tachyon, but you don't have supersymmetry. And that's the non-supersymmetric heterotic string. So you're right. There might be other things, but there are not many. You can count them with a hand, and the 5 fingers are more than you need for the projections you can do in 10 dimensions. I mean, people have been playing, and precisely now. So in 9 dimensions, you can do more things, but yeah, in 10, there is not much you can do. Yes. Because you can. Yeah. Well, I mean, it can be unsatisfactory if you want. I mean, I don't think that. So the theory without that projection is not consistent. You have this tachyon and yeah, and it's not that you can. Well, because yeah, so you have this tachyon and it's a problem. And in the heterotic string, in these non-supersymmetric projections that you can do, there are 5 different ways to get 5 different? No, sorry. No, 5 different in total. In the heterotic, I think it's only one where you get rid of the tachyon. Yeah, the other 4 have tachyons. What am I going to say? Well, I lost the yeah, I mean, this is something you can do, and it gives something nice, and it's something consistent. And there's also, yeah, I have to tell you about anomalies, because it gives you something consistent means the scattering amplitudes, everything, and then there is the anomaly question, which is a big question, and I will say a few words. So that's a big part of it. You want to get an anomaly-free theory, and now space-time anomalies, the ones I will care about. And and again, there's not much you can do. Yeah. You have a, no, it's a kappa projection on the spinor. Yeah. And in the pure spinor is a pure condition of the spinors. Yeah, I don't think you have it. Yeah.
We use supersymmetry. Now the theory is defined regarding critical dimension. Why is it that we still want to keep the supersymmetry at this stage?
No, so yeah, I could have motivated in a different way. We want to have a consistent theory. And it turns out that the consistent theory is supersymmetric. But again, you can do projections on the there's also the open, the non-supersymmetric. I mean, there are also projections that have maybe not. Let me not enter in the details because I might confuse you. But yeah, again, there are projections that don't keep supersymmetry, but there isn't much one can do that gives you something consistent, anomaly-free, and everything you want. Yes. Well, yeah, I don't know.
So we study the spectrum and we get the target and by using the slope projection, what does it mean? We are in a stable wave.
No, you are in a stable vacuum, and this tachyon is just gone. Yeah, it's not in the spectrum. Yeah. In the bosonic string, yeah, it's not so obvious. It's not so obvious why couldn't one project, but yeah, somehow one cannot. Yeah, I don't know. One could say that the number of alphas has to be odd. Yeah, it's not obvious, but yeah. Yeah, I get, but yeah, okay, it's not obvious. Yes. What? Yeah, it will. Yeah, yes. Yes. Yeah, I'm going to talk about that, yeah. Okay, let me at least write what's the projection in the Ramon sector, though you guessed it. Is the gamma, where this is, I don't know, gamma 11, if you want. This is the product of gamma 0 to gamma 9. And it has, no, it doesn't have an I. Yeah, it doesn't have an I. So chirality. So you require chirality, chiral spinors. And then for consistency, you also have to put this -1 to the F. For consistency of the whole thing, you have to project the chirality of this has to be different. So whether you choose positive or negative chirality for, let's say, the ground state is a choice, but then this other should have the opposite chirality. Here I should have the opposite chirality. Okay, so now with this GSO projection, so I got rid of this. And here I will have only one chirality. So one chirality in 10 dimensions, but if you remember, so this A Ramon was, so this chirality was fixed. and then plus minus 1/2, plus minus 1/2, plus minus 1/2, plus minus 1/2. If I want the total chirality fix, then I need to have an even number of pluses here, and that means a positive chirality in a dimension. So here you are projecting out this C. And from this, we will get 128 states. And here we see this triality planar, so the spectrum is supersymmetric, and so then the 8 vector has the same degrees of freedom as the 8 spinor, and in this triality, the other 8 is this 8. And yeah, indeed, 8 is a nice dimension. Okay, and if we concentrate on the massless sector, this is the quanta of the gauge field, A mu. Champaton degrees of freedom, I pull them out of the hat, it's 4:45. You are happy to swallow this, the Champaton degrees of freedom. So actually this 0ns is a scalar, but it has this Champaton degrees of freedom. So it's in the adjoint of UN, and if you think of this as having n branes. So it's a scalar from the point of view of SO1,9, but it's in the adjoint of UN. And this is its superpartner, so this is called the Gaugino. Lambda G. For Gaugino. So a gauge field and a Gaugino. Yeah, I wanted to do, if we do a break now and we do closed strings, then I won't get too much to talk about dualities. Okay, let's do a break, but I'll do closed strings quickly, and it's not complicated. It's tensor product of open strings. But okay, let's take 5-minute break. So one thing I forgot to. So I put the Champaton degrees of freedom in the gauge field, and I forgot to put them in the Gaugino, but the Gaugino also has Champaton degrees of freedom, right? It's a superpartner. Okay, closed string spectrum, and remember we said we have RR, NSNS, RNS, and NSR. And it's just tensoring a Ramon state on the left and a Ramon state on the right, and NS state on the left and NS state on the right. So we are going to leave them there. And we will just do the massless sector. But so if we, so remember we have the L0 phi equals A phi, L0 tilde phi equals A phi, A tilde phi, because if you are, for example, in the RNS sector, A is not going to be equal to L tilde, A tilde. So in general, it's good to do the L0 plus L0 tilde condition and L0 minus L0 tilde condition. It's the same. You can do them separately, but it's just... so in both cases, you get two equations. It's nicer to do them this way. So the equation, so this is doing L0 plus L0 tilde, what you get is, like in the bosonic string, so 2, in the closed bosonic string, the mass square of the states is 2 over alpha prime, n plus n tilde, minus A tilde. And the L0 minus L0 tilde condition says that n minus A is equal to n tilde minus A tilde. So if you are in RNS or NSR sector, n doesn't have to be equal, but shouldn't be equal to n tilde. And we have to do the GSO projection. And there was a question, so in the NS sector, the fact that the projection has -1 to the f plus 1, there is no convention there that I can change because I want to get rid of the tachyon both in the left and on the right. But in the Raman sector, indeed, why do I choose for the ground state, why do I choose positive chirality or negative chirality? So that's a convention. I could have chosen for the Raman sector a minus sign there. That's a convention in the open string. In the closed string, without loss of generality, so I can take on the left the convention that I'm taking states that are positive, that have a positive eigenvalue under this G. But then on the right, I can do two things. I can take the spectrum that have positive chirality, the vacuum on the right, or the one that has negative chirality. And that gives rise to two consistent and a priori different string theories. So the GSO projection in the NS sector is G equals -1 to the f plus 1. G tilde equals -1 to the f tilde plus 1, where f tilde is constructed exactly like f, but with the tilde oscillators. In the Raman sector, so I constructed the same way, -1 to the f, and G tilde, I also say that is gamma -1 to the f tilde, but I take G phi equals phi, and I can take G tilde, so in the Raman sector, or let me put G tilde phi Raman equals phi Raman, or G tilde, and so this is for NS or for Raman. So, but here then I choose this positive, and here I can choose this to be so G tilde phi NS equal phi NS. There is no choice. But here I have these two choices. This choice where you take same chirality on the left and on the right, this is a type 2b string theory, and this is the type 2a string theory with different chiralities on the left and on the right. So let me just, so one can build the whole spectrum. Let's just build a massless spectrum. And let me put here type 2b, here type 2a. Here NSNS sector, RR sector, NSR. No, I want RNS and NSR. So in the NSNS, we just tensor. So I can erase everything else because that's all we need. I mean, that's all we need for this, to construct the massless spectrum. So in the NSNS sector is, so I do, so E mu, I can put tensor, let me put E mu nu, B mu minus 1/2, B tilde nu minus 1/2, on 0 NS NS. And here is the same, in the NSNS. And massless to tensor, in principle no symmetry between mu and nu. This is the same as in the closed bosonic string. So from here, I'm going a bit quick, but if you, I mean, you can repeat all we did for the bosonic string, and it's, so from here you get the metric, the B field, and the dilaton. You make symmetric, antisymmetric, and yes.
How do you construct the bicycle being that?
Yeah. So with that, so I'm going to, I mean, so the projection on the right will differ. So you can do the whole tower. I'm just going to do the massless part. Okay, Ramon, in type 2b, so in type 2, on the left, I always take positive chirality. Now the notation is going to start being more and more horrible. And so this Ramon, and I tensor it with another spinor with the same chirality. So this will be, N8 S times 8 S. And we'll see, so this is not any reducible. So this 64 is 64 degrees of freedom. They are bosonic because it's fermion times fermion. It's not an irreducible representation of SO8. So we'll have to work this out. And in type 2A is N8S times N8C. Yeah. Let me call this B dot, just, so, but this is N8S times 8C. And again, we'll see what those are, the Ramon fields that were not there in the bosonic string. So this we have to, I mean, none of the rest was there in the bosonic string because there was no Ramon sector. RNS, so you just tensor this with the massless NS, so some E tilde mu minus 1/2 on 0 NS. From the point of view of representations, this is N8 S tensor N8 vector. So this is another 64, which is a spinorial representation and it's not irreducible. So we'll go, so here it was an 8 vector. So this was an 8 vector, tensor an 8 vector. And this decomposes into symmetric, which is 8 times 9 divided by 2, 36. Antisymmetric, 28. No, 35 because it's a symmetric traceless, I will forget. 28 plus 1. Right, those are the irreducible representations of SO8. And here in type 2A is the same because the Ramon is taking, so on the left side, I take always positive chirality. So this is the same guy. E mu, B mu, minus 1/2, 0, NS. So this is also an 8S, 8S times 8V. Sorry? B mu tilde, yes, thank you. Yes, yeah, please correct my mistakes. And in the NSR, so this is E mu, B mu, minus 1/2, 0, NS, tensor A, R, while the other has, in type 2A, I have an 8 dot. So E mu, B mu, sorry, and this is a bit small. So this one here is an 8 vector tensor 8S, and this is an 8 vector tensor 8C. Yes, a horrible notation. This means N8C, negative chirality in 8 dimensions. Yeah, it's this guy that. So in type 2B on the right side, instead of taking this guy, type 2A on the right side, instead of taking this guy, we take this guy when we do the GSO projection. Let me erase this. Okay, let me leave the Ramon for the end, though since we saw forms, it's not going to be long. But let's do the RNS sector. So in both we have 8S tensor 8 vector, and this decomposes into 56S plus 8C. So 56S is a spin 3/2, so the vector and the spinor, and this is the gravity, no? The super partner of the graviton. It has a vector and a spinor index. And it's sort of traceless. If you put some gamma matrix, let me not write it. It's not 64 degrees of freedom because this is like the trace of that. And this is called this lambda A dot, because it's the other chirality. This is called the D Latino. So these are the super partners of graviton, B field, and dilaton. So it's a bit, there is no BE, no. The super partner of the dilaton, so the dilaton is 1 degree of freedom and this is 8. So I mean, it's the whole thing that whose super partners are the whole thing. So this is the same for type 2A and type 2B. And in the NSR sector, which is 8 vector. So here I'm doing type 2B, and here type 2A. So we also get a gravitino and a dilatino and same chirality, while in the NSR sector we have 8B times 8C, which is, times 8S in type 2B, and this is 56S plus 8C. So we have a second gravitino. So this psi mu A, and this let me call 2, and this I call 1. And we have a second dilatino. And here I also have a second gravitino and a second dilatino, except that the chiralities are the other way around. So this is psi mu A dot 2 and lambda A 2. So I have two gravitinos of different chirality in type 2A, and in type 2B I have two gravitinos of the same chirality. And we didn't do the physical state conditions, but the physical state conditions apply on the left and on the right. So the physical state conditions of this will give me the Dirac equation. So the chirality, when we put an 8S, we already assume that the chirality along K is fixed, and the GSO projection tells us that we have a single chirality. So that's why there are only 8 degrees of freedom. And this is an 8 vector because this has to be orthogonal to K, and because of the null states. So, but if we look at the null states, so this thing that is E, in this A I could put a polarization. So I could have a linear combination of, my ground state could be a linear combination of the different, spins. Up, or up, and two downs, because the chirality has to be the same, right? But, so I can, so the same as I put so in this A, Ramon tensor E mu, B mu minus 1/2, 0 NS. I could also put here some sort of polarization tensor. So here I'm doing a linear combination of oscillations in different directions. Here I'm doing a linear combination of spins. And so this was tilde. So this EA tensor E mu tilde, let me call it E mu A. And because this E mu tilde had, because of the null states that have polarization along K, this is the same. So I call this E mu A, and this is the same as E mu A plus K mu, and some epsilon A, where this is a spinor and 8S spinor. So if we go to the field, the gravitino, this is saying that psi mu A is equivalent to psi mu A plus d mu epsilon A. Well, A up, so down. And you've seen this No? You didn't see this in the supergravity lectures. So this is a transformation of the gravitino when you have local supersymmetry. So this means that this redundancy that I call lambda in the case of a gauge transformation, A mu. So this is a spinor. The K mu is a derivative. So this means that we have local supersymmetry. Well, first that we have supersymmetry in space-time. Well, this we know. We knew that we had supersymmetry in space-time. But the fact that we have gravitino and its transformation, or its gauge redundancy, this transformation and the supersymmetry is like this, means that we have local supersymmetry. And we have two gravitinos. So in space-time, each one will have a supersymmetry parameter associated. So in space-time, we have n equals to 2 supersymmetry. So that's why these are called type 2. Yes.
What would be so EA plus E tilde was supposed to be broken into the gravitino and the dilatino.
Mm-hmm.
But you remove the gravitino.
Yeah, good. Because this thing is traceless. So if you multiply by some gamma, this is traceless. If you multiply by a gamma mu, so the condition should be that gamma mu k mu epsilon a is equal to 0. And so this is traceless in that sense, and this is trace. That's the thing that corresponds to the gravitino.
Why do you choose an equal sign? Is this E mu A?
This, Yes, yeah, good. Sorry. So yeah, that's not a. Let me not put an equal sign. So this is a part of the gravitino. Yeah. So this gives rise to this, and it gives rise to some. I don't know how to call it. Any double tilde a dot, which is the trace. So I mean, one can do that decomposition. It's not hard, but let me not do it. And this doesn't inherit any redundancy. The redundancy is all here. And that's, sorry? So the dilatino has, this 8 degrees of freedom, and there is no, I mean, you mean, sorry, yeah, that's, sorry. I didn't understand what you meant. That's the polarization of the dilatino, yes. Sorry, yes. Okay, and this is true in type 2a and type 2b. They both have n equals to supersymmetry, but so type 2b, one can write it as an n equals 2, 0 supersymmetry, like both supersymmetries have the same chirality, while type 2a, one can write it as n equals 1, 1 supersymmetry. So the second gravitino will transform with the supersymmetry parameter that has the other chirality. Okay, and in the Ramon-Ramon sector, So this A, let me call it psi A to make it more look like a spinor. I mean, yeah, I'm not sure whether to give you the result. I'll be quick. So this, you have tensor product of xi and xi tilde. These are 2 to the d over 2, 2 to the d over 2 degrees of freedom. Then, well, Majorana, y, whatever. So this is 2 to the d degrees of freedom. And this is the same number of degrees of freedom that you have if you do this. You take all the bilinears of the spinor. So this was a bispinor. Now this is a scalar. This is a one form. This gamma mu nu means antisymmetrized. Gamma nu antisymmetrized. So this is a 2 form. And this is a d form. So here, if you count, you also have 2 to the d degrees of freedom. So bispinors are the same as sums of forms. And yeah, I could do the whole thing. It will take me, I don't know, maybe 5 minutes, but every minute is precious. So when you take 2 spinors of the same chirality, like in type 2a, so this is equal to 0. So if psi tilde and psi have the same chirality, then you get only things with an even number of gamma matrices. And the opposite, if they have the opposite chirality, you get something with odd number of gamma matrices. So what you get are forms, and these are the Ramon